Hey everyone, and welcome. Today, we're diving into the invisible but incredibly powerful world of electrostatic potential energy. It's the hidden energy that literally holds atoms together, and it's what gives a lightning bolt its incredible punch. So how does it all work?
And that's a fantastic question, right? I mean, we've all felt that crackle of static electricity, maybe a zap from a doorknob, but how on earth does that simple annoyance translate into a real, storable, measurable form of energy? Well, that's exactly what we're going to unpack, step by step. Okay, so to get our heads around this, let's start with something we all intuitively understand: gravity. So picture this. You lift a heavy rock off the ground. You're putting in effort, right? You're doing work to fight against gravity. But that work doesn't just disappear. Nope. It gets stored in the rock as gravitational potential energy. The higher you lift it, the more energy it's got stored up. Now, believe it or not, it's the exact same idea with electric charges. When you try to push two positive charges together, they naturally want to fly apart. The work you do forcing them closer gets stored as electrostatic potential energy in the electric field between them. Now, the only reason we can even talk about storing energy like this is because of a really cool property of forces like gravity and electrostatics. They're what we call conservative forces. And what that means is it doesn't matter how you get from point A to point B. You could move an object in a straight line, or you could take some wild, loopy path. The total work done against the force is exactly the same. The path is irrelevant. And it's this path independence that makes the whole idea of potential energy so reliable and useful.
All right, so let's take this concept and put it into action. We're going to run a little thought experiment to actually see this energy get stored.
Okay, take a look at this diagram. It sets up our whole scenario. Imagine we've got this big stationary charge, which we'll call big Q. Think of it as our source. It's creating an electric field all around it. Then we bring in this little guy, a tiny test charge we'll call little q. And our job is to push Q from point R over to point P, getting it closer to Q. So let's get to know the cast of characters in this little drama. First up, big Q. That's our source charge, just sitting there at the origin, creating the electric field. Then there's little q, our plucky test charge, that we're going to move around. Now, since they're both positive, Q is pushing Q away with a repulsive force, which we're calling F sub E. To fight that push, we have to apply our own force, an external force, F sub X. And R and P, they're just our starting and finishing lines. Okay, concepts are great, but physics is all about quantifying things. So let's roll up our sleeves and look at the math. How do we actually calculate the work we're doing and the energy we're storing?
Whoa, okay, don't panic when you see this equation. That big curvy S thing, that's just an integral sign. It's really just a fancy math tool for saying add everything up. All this formula is really saying is that the total work we do, W from R to P, is what you get when you add up every tiny little push, that's FXT, over every tiny little step, that's DR, you take along the entire path.
And here it is. This is the magic connection. The work we just figured out how to calculate, WRP, is precisely equal to the change in the system's potential energy. That's what the delta U means. It's a perfect one-to-one trade. The effort you put in becomes energy stored in the field. It's that simple. All right, theory's great, but let's plug in some real numbers to see how this works. As you can see in the table here, we've got our values: a source charge Q, a tiny test charge Q, and our start and end points. We're going to push that charge from 10 centimeters away all the way into 5 centimeters. With these numbers and Coulomb's constant, which is just a universal number, we can actually calculate the work done. And crunching those numbers, this is what we get: positive 0.00018 joules. That's the amount of work we had to do. And because of that perfect energy transfer we just talked about, it means the potential energy of our little system went up by that exact same amount. The reason it's positive is key. We had to push against the natural repulsive force, so we were actively adding energy into the system. Okay, this is all making sense. But now we've hit a really subtle but super important little problem. So far, we've only talked about the change in energy between 2 points. But what if I just want to know the energy at one single point? And that's the million-dollar question, isn't it? We calculated the energy difference between R and P, but what's the absolute energy at P? It's kind of like asking, how high is this table? Well, high compared to what? The floor, sea level, the center of the earth? You see, you always need a reference point, a zero, to measure from. And this quote from a textbook really nails it. It says,
What is physically significant is not the potential energy, but only the difference of potential energy. What that means is nature doesn't care about the absolute number. Nature only cares about the change, because it's the change in energy that creates forces and makes stuff happen. And this fact gives us a ton of flexibility.
So physicists came up with a really clever solution. Since only the differences matter, they said, hey, let's just all agree on one place to call zero. And for charges, the most logical place is infinity, way out where the charges are so far apart they can't feel each other's force at all. So by convention, we say the potential energy at infinity is zero. Boom! We now have a universal benchmark to measure everything against.
And that simple agreement gives us our final, clean, practical definition. The potential energy at any given point P is simply the total work it takes to haul a charge all the way in from infinity, our 0 point, to that specific spot. So U at point P is just the work done from infinity to P. It's elegant and it works everywhere. Awesome. We've covered a lot of ground. So let's pull it all together and summarize the key formulas and the big ideas you should walk away with. Okay, here are the key equations to keep in your back pocket. First, the work done is the sum of force over distance. Second, and this is the big one, that work equals the change in potential energy. And third, thanks to our 0 at infinity rule, the potential energy at a single point is just the work it takes to get there from way out in deep space. And conceptually, here's the story. 1. Potential energy is a special property of conservative forces like electrostatics. 2. It's basically stored work. 3, and this is so important, only the difference in energy actually matters in the real world. And 4, to make life easier, we all agree to set our 0 energy baseline at infinity. So, where do we go from here? We figured out the energy for one charge in the field of another. But what happens when you have a whole bunch of them? How do you calculate the total stored energy of an entire system of charges, like all the atoms buzzing around in a single molecule? Answering that question is the key to understanding the energy that holds our entire world together. And that's exactly what we'll explore next. Thanks for joining me.